Good afternoon, everyone. This is Angelique Reyes Quinones from DCPET 32 for the Microprocessors Lecture Finals presentation, and this is entitled Processing Powers. But before we proceed with that one, let us ask, how does a CPU work? So CPU, or the Central Processing Unit, is the primary component of a computer. Through a series of stages, it will execute instruction and also data processing. And here are the core components that make up the CPU. We have five, and for the first one, we have control unit, or the CU, which is using the signal produced by other components in order to direct data flow and interpret the instruction. Second, we have ALU, or the arithmetic logic unit. This is the one responsible for executing the mathematical operations such as addition or subtraction. We also have logical comparison such as and or. Third, we have registers, wherein these are high-speed memory units and small amounts of data get stored in these registers. As an example, we have address register or memory address register and also memory instruction register. Next, we have cache. In order to reduce access time, cache serves as temporary memory for those data that are frequently being accessed. Lastly, we have the clock. This emits electrical pulses at fixed frequency, and this helps in synchronization of operations. And in order to execute these instructions, the CPU follows a four-stage cycle. So we have fetch, decode, execute, and write back. For the first stage, we have fetch. Using the program counter, it retrieves instructions from the memory or the cache and locates the address. Second stage is decode. This translates instructions into binary signals so that the CPU can interpret the instruction. And third, we have execute. In the ALU, operation or the calculation is performed or data gets transferred to other components at this stage. And for the fourth stage, we have write back. All the results will be stored in registered or in a cache or at a memory for future use. Key functions of CPU, we have four: parallel processing, interrupt handling, memory management, and clock speed. So for parallel processing, nowadays modern CPUs are already capable of being multi-core, which allows the CPU to divide the task among the cores. And using the pipelining, CPU is now able to process multiple instructions simultaneously throughout the stages in the cycle. Next, we have interrupt handling, which is or wherein CPU is capable of pausing temporarily to respond to urgent signals from either hardware or software. This also means that the CPU can get back to the pause task after the interrupt. Then we have clock speed. This determines how many operations the CPU can complete per second. And at this time, it is now measured using gigahertz. And modern CPUs are now reaching 5 gigahertz. This means that um, it is also, or the 5 gigahertz is also equivalent to 5 billion instructions per second. Okay, for evolution of CPU, revolution in miniaturization happened mid-60s or 1960s. The development of ICs began by packing multiple transistors onto a single silicon chip. This innovation laid the foundation for modern electronics and computing, revolutionizing the society. In 1971, the Intel 4004 CPU has been founded. The first commercial microprocessor, which is Intel 4004, had 2,200 transistors, and initially this one is for a calculator of BusyCom, and it was later released to the public. This is capable of executing 46,250 to 92,500 instructions per second. This only consumed 1 watt of power, which was 3/4 inch in size, and cost about $5 to produce in their time. Evolution of processing power happened in 2017 because by 2017 CPUs like the Intel Core, which is now i9-7980XE, could execute over 80 billion instructions per second compared to the Intel 4004, which was only capable of executing 46,000 to 92,000 instructions per second. In understanding how a CPU works, CPU use binary bits 0 or 1 to represent data, and multiple bytes create a word, 32-bit or 62 or 64-bit, which defines the processor's architecture. Instructions are the fundamental operations a CPU performs, for example, adding numbers or moving the data itself. Complete set or complete list of instructions a CPU can execute is called an instruction set. And in RISC pipeline, RISC, basic CPU operation is here. We have fetch, decode, execute, cycle. For the fetch, the CPU retrieves an instruction from the memory called RAM, and after that, it decodes the instruction. The instruction is broken down into an opcode, which is called the operation, and the operands, where the data is to be operated on. And then after that, execute, the CPU performs the operation. And in the 1970s, here are the advancement of CPU designs. CPUs became more robust with faster clock speeds, larger address capacities, and complex instruction sets. So in 1972, Intel 8008 has been introduced, which features 14-bit address capacity, expanded instruction set, and more registers. This has inspired Bill Gates and Paul Allen to build a traffic data computer, leading to the founding of Microsoft. In the 1970s, was the interrupts also introduced. Hardware signals and internal CPU events could pause program execution from high priority tasks. And competition and evolution. Zlog Z80 designed by a former Intel engineer became a strong competitor. Intel responded with the overambitious 8800 IAPX 432, which failed commercially. And in 1978, Intel 8086 marked a major milestone with the introduction of the x86 architecture. This has a fully 16-bit CPU with 20-bit address capacity supporting up to 1 MB of memory, set the foundation for modern desktop CPUs. Complex Instruction Set Computing, or CISC, the 8086 cemented Intel's commitment to CISC architecture, enhancing the complexity and capability of instruction sets for future processors. But there are limitations to the CPU arithmetics. CPUs handle basic arithmetic via the ALU. Advanced math involving decimals was inefficient since floating point numbers were incompatible with standard CPU arithmetic hardware. So in the 1970s were the introduction of floating point numbers as well. They were developed to encode decimals in bits, but early CPUs processed them inefficiently in software. So 8087 floating point coprocessor. Intel created this coprocessor to handle floating point processing hardware, which worked with 8086 CPU. This intercepts specific instructions and perform floating point operation independently. It is already capable of performing addition, subtraction, multiplication, division, square roots, and transcendental functions, which are exponential, logarithmic, and trigonometric. This can also execute 50,000 floating point operations per second. And then after that, the IBM PC and the 8086 or 8088 processor. The 8086 processor success was tied to the IBM PC, which used the 8088 variant. IBM entered the market with the IBM PC, launched on 1981, August 12, after a rapid 12-month development cycle. And here are the impact of the IBM PC. The IBM PC was actually small, lightweight, and easy to use, which targeted individuals and not just enterprise or corporations. This sold over 40,000 units upon release and 100,000 units sold in the first year. This has surpassed the Apple II as the best-selling personal computer of the time. So here would be the Microsoft role. Microsoft was contracted to develop the IBM PC's operating systems, PC-DOS or DOS. This became Microsoft's first major product, propelling its rise to dominance in the software industry. Standardization of the PC. The success of the IBM PC led to the creation of IBM-compatible machines, and wide range of hardware and software were also developed in order to support this new platform. The IBM PC also became the standard in personal computing, evolving over time but maintaining dominance. And the legacy of 8086. The architecture of 8086 has had a lasting influence on modern personal computers and servers. It continues to power the prevalence of PC architecture in today's computing landscape. Multitasking evolution, multiprogramming in the 1960s to 70s were the early form of multitasking, processing programs in batches, switching during hardware input waits. Um, for the time sharing, real-time switching between processes exemplified by IBM's system. True multitasking in the late 1960s emerged in systems like DEC's PDP-6, IBM's OS 360 MFT, and Multi-CS, the latter influencing Unix development. Transition to personal computers, growing demand for multitasking led CPU manufacturers to integrate multitasking support into processors, bringing it to personal computing. Memory management in multitasking. Memory Management Unit or MMU is the hardware that manages memory allocation, protection, and access permissions. Memory protection has prevented processes from accessing unauthorized memory, ensuring system stability and security. Privilege levels in gates, which are OS kernel, and operates at the highest privilege with controlled access to system resources via APIs. Virtual memory has also been introduced here. That concept is that the virtual memory maps logical memory addresses to physical locations, enabling flexible memory usage. And it was also introduced the graphical user interface. First, they had Apple Lisa in 1983. This introduced a mouse-driven GUI and used the 32-bit Motorola 68K CPU, but faced poor sales. And then in 1984, Apple introduced another GUI, which is Macintosh. It's an improved GUI from Lisa, initially limited to single tasking, but later on supported true multitasking. 1985 Macintosh and desktop publishing. Apple's partnership with Adobe introduced desktop publishing, helping Macintosh become a major IBM competitor in the early 1990s. Competitors like Commodore and Atari also offered GUI-based multitasking but were less successful. Now we have the microprocessor Motorola 68K, which was widely used in the 1980s due to its powerful architecture, becoming a strong x86 competitor of Intel. This featured 32-bit internal architecture with 8 general purpose and 8 address registers with limited to 24-bit external addressing, which allows 16 MB of RAM. IBM PC-80 and the Intel 8286 processor in 1984. This introduced protected memory mode supporting multitasking. Microsoft Windows 1.0 debuted in 1983, running on top of MS-DOS, introducing GUI and cooperative multitasking, setting the stage for the Microsoft-Intel partnership. In Intel 8286 innovations, first mass-produced processor supporting multitasking for multi-users, included robust memory management unit for memory protection, privileging, and virtual memory. It has also eliminated multiplexing on data or address buses for faster processing, dedicated address unit for memory addressing, freeing the ALU resources. This microprocessor also improved instruction prefetch unit with basic pipelining, speeding up instruction execution. And multitasking interrupt handling has also been introduced here in this Intel 8286. Um, in the evolution of the architecture x86, the features introduced in the 8286, particularly protected mode and multitasking capabilities, laid the foundation for the evolution of modern x86 processors with advanced multitasking and memory management features. And now let us proceed in 1981 for the Microsoft Word development. Microsoft has hired Charles Simonyi, a former Xerox programmer, to develop a word processor. Simonyi had earlier created Bravo, the first GUI-based word processor for the Xerox Alto. Simonyi and Richard Bode developed Multitool Word, Microsoft's first word processor initially for the Unix OS. Microsoft Word was released for MS-DOS in 1983 and was the first program built or bundled on disk with a magazine. It was among the first DOS programs designed for mouse use, but was less competitive compared to WordStar. The first version of Word for DOS was only 150 KB in size. Modern versions of Microsoft Word required at least 4 gigs of disk space and 2 gigs of memory. Software complexity has already increased significantly in the 1980s and 1990s, leading to higher demands on processors. This spurred the movement toward mainstream 32-bit processor architecture. National Semiconductor's 32016 in 1982, the first 32-bit general-purpose Microsoft, faced issues like bugs and speed limitations. Motorola 68020 in 1984, a true 32-bit successor, and was used in Apple Macintosh 2nd, Sun 3 workstations, and Commodore Amiga 1200. In 1985, microprocessor Intel 8036 introduced a robust 32-bit architecture with improved memory management and debugging capabilities, which was then adopted by Compaq. It became the standard for IBM PC compatibles. The impact of 32-bit architecture enabled direct management of up to 4.2 gigs of memory. Formed the architecture formed the foundation for modern software architecture over the next 15 years. Significance of the pipelining. Pipelining allows modern CPUs, particularly RISC processors, to achieve higher clock speeds and efficiency. This also introduced complexities like hazard management, but became a crucial part of CPU design. Meanwhile, out-of-order execution, instructions without dependencies on stalled ones may execute out of sequence to reduce pipeline underutilization during data hazards. And for early pipeline implementations, the Motorola 68020 used a traditional three-stage decoding pipeline. Meanwhile, the Intel 386 had a three-stage pseudo pipeline that evolved from the 80 to 86, which with each stage functioning as a self-contained state machine. Memory access bottlenecks and caching. As CPU speeds increased in the 1980s, memory access became a bottleneck due to slower memory speeds. Caching was introduced using high-speed static memory to buffer access to slower dynamic memory. Early cache were small. The 68020 had only 256 bytes of instruction cache. Meanwhile, the 386 reported up to 64 kilobytes of external cache. Modern CPUs have hierarchical caches for instructions, data, and address translation. Cache hits and masses. Meanwhile, cache hit is when data is found in the cache leading to fast access. However, cache miss, this means that the data isn't in the cache, requiring slower system memory access, potentially stalling or slowing down the instruction cycle. For cache replacement policies, when a cache set is full, the replacement policy decides which block to overwrite. Least recently used is a properly strategy, replacing the least recently accessed block. Software can mark seldom used memory regions as non-cacheable. Here are the cache write policies. We have write through, write back, and that's it. So for write through is when data is written to both the cache and the system memory immediately, while the write back data is written to system memory only when the cache block is replaced. Some policies batch multiple writes to optimize memory access. Now we proceed to how a GPU works. But before we go to that, what is a GPU anyway? GPU, or the graphics processing unit, is a specialized processor that can handle complex calculations, which are mostly for rendering visuals and perform parallel computations. And here are its core principles. We have parallel processing powerhouse, dedicated memory system, and task specialization. So for the first one, GPUs are a powerhouse of parallel processing. This is because GPUs contains thousands of processing cores, unlike the CPUs which only have 4 to 16 cores. This allows the GPUs to perform tasks simultaneously. Dedicated memory system, GPUs are now at GDDR6 or GDDR6X VRAM, which is around 900 GBps, and wide memory buses at around 256 to 384 bits. This enables data access further than rapid. For the task specialization, here are the tasks that the GPU specializes. We have graphics pipeline, processes that includes 3D scenes, also with stages. Compute operations, which are great in AI or in machine learning workloads. Lastly, the ray tracing or RT, which is the GPUs are having dedicated RT cores for realistic lighting. And now we have SAP1 operations. SAP1, also known as simple as possible, it is an 8-bit architecture which is designed to perform fundamental computing principles. It is executed through 6 stages at every step, having the fetch execute cycle. With that said, the fetch cycle is from T1 to T3 and execute cycle is from T4 to T6. So here are the supported operations of SAP1, which is 5. You have LDA, add, SUB, out, HLT. So first is LDA, which is load accumulator, which is having the opcode of 0000. This loads the accumulator with data from the specified RAM address. Meanwhile, the add simply means add to accumulator, have the opcode of 0001. Data from the specified RAM address is added to the accumulator. Then third is we have SUB or subtract from accumulator. It has the opcode of 0010. This subtracts data from the accumulator with the help of the specific RAM address. And now we have out, which stands for output and has the opcode 1110. It copies the value from the accumulator to the output register, and this can also be outputted to a display. And lastly, we have HLT or halt. It halts or stops all the processes and has the opcode of 1111. And that's all for this presentation. Thank you so much.